Hello everyone, this is the Great Fez and back with the second video on my Ascent Program Evolution series. Today I'm going to be talking about the gravity turn. It's pretty awesome. I love to use it, but eventually I decided against it, and I'll go over all those details. But before that, I want to talk about a couple changes. I updated my headset, so I got a new one, so hopefully the mic is a little better. Uh, the action items are now added onto the presentation so you can actually keep track of what exactly I did between each step, as opposed to, having to go through the code or anything like that. So before we ended on version 1.2, which was just a linear algorithm, and then the action items that I created are to convert to a gravity turn algorithm as opposed to a linear algorithm, and we're going to be outputting a little bit more variables for better clarity and stuff. So um, before I do that, I want to clarify what a gravity turn is. A lot of people um, use the term gravity turn as synonymous with ascent profiles, and a gravity turn is not an ascent profile. It is a guidance control scheme. It's used to turn a ship in a certain method. It's like a maneuver, like pulling up on the stick or anything like that, but it's not a given ascent profile. The ascent profile is a set of commands based on pitch and yaw, and you know a gravity turn does not have those kind of parameters in there. What it is though is a definite method to optimize a trajectory, right? So if it, in any rocket is always run through simulations, and if you a using a gravity turn, you can actually have minimal inputs to then determine what is the most optimal trajectory for whatever it is you need, right? You can determine using the gravity turn method, you can optimize it for efficiency, for payload delivery, all kinds of stuff, whatever it is that you're looking for. And lastly, it is definitely not the most optimal method. It is a way to optimize. It is not the most optimal. The most optimal is very, very broad, is very obscure. It could be a total number of things. It's all dependent on the ship's parameters, how much thrust it has, the different stages, the masses. All that goes into determining what the quote unquote most optimal is. And on top of that, it's not always just about efficiency. You could be trying to minimize the stress on the vehicle, all kinds of stuff. So just to clarify those things, so when I talk about a gravity turn, I'm not talking about the ascent profile. I'm just talking about the scheme. The scheme that I will be using for this analysis, this little experiment, is that it'll be a pure gravity turn. So that means that the ship is going to pitch over a little bit and then literally just follow prograde all the way into orbit. Um, and that's typically called, or I call it a simple gravity turn. It's also called a pure gravity turn. You see those used a lot. So this is the methodology of how a gravity turn is performed, and you can actually hear this be called like in real life launches. They don't like I said, they have a more robust ascent profile, ascent program, but they still follow this sort of methodology. First thing you do is ignite the engines, accelerate vertically. Once you reach a certain speed or altitude, usually you have to pass the towers there, the launch towers. Once you do that, then you pitch over and give it a pitch kick, or sometimes called a pitch over maneuver. All that stuff. Essentially, you're just turning the ship just a little bit to downrange, and then from then on, you maintain zero angle of attack throughout the ascent. So, to illustrate a little bit more of how that works, and uh, pull out a nice Wikipedia page on this. You can read a lot more about its uses and history here, but if you look at this diagram, you can see that gravity is being directly applied through the velocity vector, right? So it's like if you had a rope pulling down on a ball that you threw up, or a rocket, it's just you're essentially just holding it down. So it's going to accelerate, but it's just working against you. You're not turning it. However, if the rocket was actually flying sideways, if you think about it, if you had a rope on it and you're pulling on it, you're going to be turning that rocket as it accelerates, right? Even though there's gravity is just pulling through the center of mass, the velocity is still going to be changing and rotating as it increases. So you can see here this angle here, the velocity is smaller. The angle is smaller than this angle. So as it accelerates, the velocity increases, but it's also pitching down. So that's what's going to be happening is as you're ascending and you're going through the atmosphere, your velocity is going to be pitching over and over at a constant rate that's determined by a bunch of parameters here. Let me uh, zoom in here. I wanted to give you guys an intuition about how this works. So first off, this right here dictates the rate at which you're pitching over. So if we hold this right side constant, we see that this velocity term means that the higher your velocity is, the lower that you're going to be pitching over. And you can think about that as something that's going really fast is very hard to pitch over, but instead of something that's going very slow. The second thing is that this sine beta right here, this means that if you're pointed vertically, you're not going to be being pitched over at all, as we explained before with the diagram. But the farther over you're pitched over, the more that gravity is going to be turning you, right? So as your pitch angle increases, your rate is also going to increase. And then lastly, right here, this term is how you determine, the acceleration of the ship. But essentially, the intuition that you should pull out from here is the higher your thrust, the less that you're going to be pitching over. So the slower you're going to be pitching over. If I'm not mistaken, up here somewhere it talks about throttle. Um, somewhere. Oh shoot, I probably should have found it before. But essentially, you can actually use the thrust to um, control the pitch of the rocket, right? So um, that's what a gravity turn is. That's how it behaves. Now we're going to implement it, and I'm going to show you how I did it. All right, first, let's just go over the last thing that we did. We had this linear algorithm here. We had this one print statement. So we're going to be adding more print statements, and we're going to be changing this to a gravity turn. So check out GTU 0. Date this. And now we can go through what we changed. So first thing that you can see here is this is just a touch base. This is how I do all my outputs. It's very crude. It's just line by line, but you might be interested in this methodology. I use this line input for each one, and then every time I add something new, I just increment it by one. So that means that I could easily switch this from putting it here to down here. I could just add another one. I don't have to adjust every single one of these. It automatically adds another line there. So it just makes it easier to print stuff out, and it's something you might be interested in. The other inputs that have been added is this switch alt is the same as before. It's when we start pitching over. This pitch over angle is how far I want to pitch the ship over. And this pitch hold time is how long I want to hold the ship at that pitch over angle. And then this gravity turn is essentially a latching mechanism so that I don't go through this if statement again. And then the way this logic works is we start off at pitch equals 90, so straight up. Once the altitude reaches the switch alt, and of course you haven't already pitched over, you're going to set the pitch to pitch, which is currently set to 90, minus pitch over angle, which is 3, so it'd be 87. And then we're going to wait those 2 seconds, and then lock steering to surface prograde, set this to true, and then we're never going to go in through here again. So we'll just be following the surface prograde all the way up. So let's run that. I want to point something out here that we're going to be looking to fix. So we're accelerating, we're waiting for the switch alt to happen, and I want you to notice how it pauses. Notice how none of these are updating, and then it switches. That's not good. We're going to be looking into how to fix that. The second thing is that now it's a much smoother approach. I'm going to rerun this, so I made you focus on the console. I want to show you now what the ship looks like as it's running. So, and I'll let this one run all the way till its end, so you can see how smooth it is and how somewhat natural it looks. But right when we hit the 250, notice how it pitches over, and then it pitches back. So it's a very small pitch, but something that you can critique about this is that it's not realistic, right? A rocket isn't going to just suddenly sharply pitch over 3 degrees and then pitch back. That's not really how rockets work. They have smooth transitions from vertical to pitching over. But once you're past that one instance, now it's just a constant smooth pitch over because we're following the surface velocity vector, and then gravity is pulling us down, which means that the velocity vector is going to be rotating constantly. And so as we increase speed, it's going to be slowing down the rate that we pitch over, but also as we increase this pitch over angle, it's going to be increasing. So it's all very dynamic, but it's very simple, right? All I had to do is just put in these 3 parameters and go on from there. It's pretty smooth. I know that this actually works. I've tested it multiple times. Once it reaches, the 100-kilometer mark, it's just going to cut off. And see if I can get it to that point. Because I want to illustrate something else that we're going to be looking at. Now it's finished, but the program has ended. This isn't really good because we still have all this atmosphere to plow through. We're still at 20,000 meters left. And that's not good. We want to maintain the surface velocity or this orientation of zero angle of attack as all the way throughout the atmosphere, because we don't want to be losing gravity, or we want to be losing drag, delta V to drag. Now, we didn't really lose that much here because we were going so fast vertically and we were already very high, but if we were to go at a shallower angle, we definitely want to be, minimizing our drag loss. That's something we're going to adjust. It's just a quick fix that is nice. So the other thing I wanted to show is just how sensitive these inputs are. So if I change this to 5 and this to 3, so all I did was just increase by 1 second and 2 degrees. It's relatively, compared to the entire rest of the flight, the entire minute or so that it was, it's very small. But I want to show what happens when I do that. Kind of accelerating here. Don't want to waste too much time while it's going. Now it's gonna be doing the same thing, but notice how fast it's pitching over. Pitching over really fast. Maybe even too fast. Yeah, this is not good. We're almost horizontal now. Uh-oh. Yeah, this is definitely going to crash and explode. But did you notice all I did was change it by 2 degrees in 1 second? It's very, very sensitive. The amount of changes that I need to make for this stuff to work, the tuning is quite annoying. So that's another thing that we're going to be changing, because I don't really have any control over the state of the rocket right after it does the pitch over. It's not very nice. The other thing is that the heading is not locked, right? Once it just follows surface prograde. If this was a real ship and you had some crosswinds that were happening and your velocity vector turned, you're no longer following you're not going to hit your intended inclination. For us, it's just 0 inclination because this is very basic script for now. But if this was in real life, when we're going to be launching from Kennedy Space Center or Baikonur or something, we have to maintain a certain azimuth to hit our inclination, and without locking the heading, we're just letting the ship wander around in the yaw, and that's not good. It does, however, have more realism than the previous ones, which is good. So I've already touched on all these critiques, so I want to go into the action items. These action items are major. These are going to be action items that I'm going to be using for the rest of my Ascent programs. So I want to touch base on them and what they do and why I chose them. The first thing is run modes. Run modes are essentially a state machine methodology. It's making your program do certain things at different states, right? So, for example, in a video game equivalency would be if you press the crouch button, you're now in a crouch mode. So whenever you're moving, you're going to be slow. Your head height is going to be lowered. If it was a shooter, your stability might be increased. Same thing with going prone. So all those are modes, and it changes the behavior of how you function. So whenever you press the move, the function move is going to be a different speed, and it's going to have different animations. So that's an example of a run mode. We're going to be using that because it makes it a much cleaner approach. We can see all the different states that the function is going to be at, and it makes it nicer for calculating pitch and stuff like that. And we can eliminate some issues and make sure that the function is doing what we want. Second thing is we already touched base on this is the pitch is going to be following the heading again. So before we use heading using the linear algorithm, and now we're going to go back to it. So we're going to be using a pitch and feeding that into the heading, so we're always pointed directly east for now. The pitch over maneuver, remember how I mentioned how it's very arbitrary? I don't know what the state of the ship is going to be after the pitch over maneuver. We don't want to have that. We want to have a way that we could determine what the state of the ship is going to be at. So, what we're going to be doing is instead of just sorry, I keep clicking. Instead of what we're going to be doing is we're going to actually wait until the velocity vector is is matching where we're pointing the ship, so the pitch angle, right? So that means that uh, we know that whenever we start our true gravity turn, the ship is going to be the velocity vector is going to be at a certain angle. That's that's much better than just saying, okay, just pitch for this long and go. At this point, we at least eliminated one point of uncertainty with all the ship designs. Um, this one again, we were touch base is about the atmosphere. This one's kind of funny. I didn't notice it until the last part, but I've been using pitch um, for my pitch parameter. But pitch is a variable that's used in KOS. We definitely don't want to be using variables that are being used in KOS. That's just good practice for any programming language. So we're just switching pitch to pitchang. Um, so that's just something that we're going to be fixed. So without further ado, let's switch out to point. Oh, yeah, forgot about that. Get checkout. So we made that one change to the parameters, and that's you have to reset them before we switch it back. So now, first thing I want to show you is now the pitch program is its own function. It's pulled out from the loop, so it's much nicer and cleaner. I'll come back to how it works here in a second. Uh, the other thing is the inclusion of run modes. So how this works is now within this loop, um, if if the ascent stage is 1, it's only going to go checking through here. If the ascent stage is 2, it only goes through this section. If the ascent stage is 3, it only goes through here. So that way I can eliminate unnecessary calculations. I can eliminate any confusion of what the ship might be doing. Different I could have different algorithms or schemes being calculated depending on the stage or the run mode. So this is a much cleaner approach. It makes the loop do less calculations. It goes through, and on top of that, remember how before it was pausing whenever it was doing the pitch over maneuver. This method ensures that you're going to be going through each section and then continue on uh, to print out all these variables. The pitch over ang is now constantly being adjusted, and this is still set to heading 90 and pitch angle. So now it's being calculated by this pitch program. The inputs are the ascent stage, the switch altitude, and the pitch over angle, and I'll show you how those work here. So if the ascent stage, if it was 1, it doesn't go into these if statements, so it's just going to print out 90, which means ascent stage 1 means going vertical. Ascent stage 2 means pitch over maneuver. So we're going to set that pitch angle to 90 minus the pitch over angle. And that's right now, the default value is 3, but I think I have it set to 2. Um, so again, if you wanted to use this, you can just leave it as 3 or adjust it here. Then afterwards, after it goes into Ascent Stage 3, this is where we're just going to be following the surface prograde. And this equation right here is how to get the angle between the vertical vector and the surface prograde. So essentially, what is commonly known as the um, uh, flight path angle. So that will give us the pitch that the ship needs to point at so that it's aligned perfectly with the surface prograde. And then lastly, this is how we're going to be checking to make sure that the pitch over is complete. So during the pitch over, that means when the ascent stage is 2, we're going to be calculating this angle check value. This angle check value checks the difference between the angle on the surface prograde vector and the steering vector. So once those are below 0.1, this is arbitrarily chosen, but essentially saying when the angle between is very, very small, then we can continue on and follow the gravity turn. And then lastly, I didn't touch on this run mode, but this is the throttle run mode. Um, Whenever we were, remember how we're also added the ability to coast, so now we're checking that both we're out of the atmosphere and that the target orbit is met. When we do want to just coast, we need to turn off the throttle. So we use this throttle stage to check, hey, is the apoapsis above the target? Then turn off the throttle and then turn this throttle stage to 2. So it will never go through this loop again and it'll turn the throttle off. Also, I added this wait till 0 so that I know that each one of these is new variables or new calculations. Wait 0 just waits for the next physics tick. And that was a lot of talking, so now let's watch it run. So I'm gonna run this initial part a couple times. The first part, I want you guys to look at the console to show you how the throttle or the stages are working. So first is when we reach 250, we're going to switch into stage 2. Notice how the pitch angle is now 88 degrees, and then it switches into state 3, and now we're going into the gravity turn. So you can see that the pitch angle is now reducing as surface velocity vector is changing. So now that you've seen that, I want you guys to watch what the ship looks like. Just want to point out one critique here, and that is that we still have that very sharp turn whenever we reach 250. Right here, see, it's quote-unquote sharp, but again, it's a very sharp turn. It's just going 0 to 3 degrees or 2 degrees immediately. We want to make that smoother. I don't, it's not really that noticeable. Again, this is a game, so it can handle it, but one of those realism things that I want to improve upon. And also, it just looks a little bit nicer if you can just have a very, very smooth transition from vertical to transitioning over. The other nice thing that we did is we reduced the number, if you notice, we reduced the number of inputs that we have to worry about. So now it's just 2. Still need to tune them per ship, but it's much nicer this way, right? Gonna warp to when we reach our destination here. Break. I just want to show the last bit. So now we cut the throttle. We're still running the script here. We're waiting until this altitude reaches 70 kilometers because that's where atmosphere cuts off. But our throttle stage is now 2, and then we're just sitting at 0. So what's wrong with this? Well, the pitch over again is first off, it's not it it's too sharp. I want to create an even smoother approach to that. Secondly, the pitch after you do the pitch over maneuver is entirely dependent on the ship's design. I don't want to. There's too many variables there for me to sit there and try and fiddle with my designs to make it work. If a ship can get to orbit, I don't want to be sitting there fiddling with the inputs. I don't want to be changing the ship design too much to to accommodate it for these inputs. It's not a good thing. The ship still needs tuning, or the inputs still need tuning. Again, it's more realistic than the previous one because now we're coasting, or it's a more realistic trying to get the ship at a certain state whenever you pitch over. So that's improved. Um, but here are the action items. This is what the reasons why I don't want to use the gravity turn. The reason why is again I don't have any way to determine where the ship is going to be, what the pitch is going to be, what the velocity, any of that stuff. I don't have anything besides the only inputs I can do to change those are the ship's design. So we're switching from a pure gravity turn to a polynomial curve, which will be a square root curve. Um, uh, we're going to start measuring the delta V gains and losses. This is just to so now we can get some parametric values and start to analyze this more scientifically to get some data to see how well are we performing. We want to get some performance measures. So we'll be analyzing the delta V gains and losses there in the next script. We're going to be developing a method for when we can decide to switch between looking at the surface velocity and switching to orbital, right? Because if we're, at 60,000 kilometers or 60 kilometers in the atmosphere, we don't really care about the air anymore. It's way too thin. So we could just start looking at the orbital frame, but we need to develop a method of when to do that. And lastly, this is by far the most important one because it's going to eliminate or start to eliminate the whole tuning problem that I have is create a framework where I can take the ship's parameters, such as the initial throttle or thrust, the stages or anything like that, and be able to auto tune the ascent profile to match the ship's design. So no matter if I have a thrust to weight ratio at the beginning of 1.1 or 2.0 or 12 stages or one stage, whatever, I can put all that stuff in hopefully, and then make it work on the ascent profile. So that's what we're going to be talking about in the following stuff video. Please, if you have any comments or questions, let me know. Thanks for watching, and I'll get back with you guys for the next video soon. Bye bye.